Hello guys, this is Code and Code and this is fourth lecture of string theory series, string algorithm series. And in this lecture we are going to see how you can calculate hash value of substring of a string in constant time, in big O of one time. So let's get started. First thing first, lecture preface. So what we are going to do in this lecture. First, uh, what is the overall idea of this algorithm? So what we are going to do, suppose you are given a string of length n, what we will be doing is that we will be pre-calculating the hash value of the string, which would require a big O of n time, and we will be also calculating some, will be pre-processing some, basically calculating and storing some modular inverse that will require analog n time, and I'll be showing you how. And uh, then after these two pre-processing, you can calculate hash value of any substring of the given original string in big O of one time. Any uh, and for hash value of any substring you can calculate in big O of one time, and the substring I'm talking about for this string. So if you have some problem statement where there is a given string and there are q queries which can be there, and each time you are required to calculate a hash value of a given substring of the original string, then there you can't just go every time and calculate hash value of that substring. That would result into TLE. If you would use normal uh, hash uh, rolling hash method. So what we are going to do in this lecture, we'll be seeing how you can calculate hash value of that substring in constant time, so that you the overall time for q queries would be q times 1, that is q, if there are q queries. So let's study the basic algorithm, the algorithm behind the big of one time operation. So in the previous lecture we have already seen that hash value using polynomial rolling hashes of a string s can be calculated using s0 plus s time 1 s0 plus s1 times p plus s2 times p square plus dash 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 sn minus 1 times p raised to power n minus 1 p, when modulo m, of course, where p and m are two primes, right? We have already seen this in previous lecture. And for example, the hash value of coding would be this. If I try to evaluate the hash value of substring din, you see, din, the hash value of din using polynomial rolling hash would be d times p raised to power 0 plus I times p raised to power 1 plus n times p raised to power 2, of course modulo m, right? Can you find the relation between the contribution of din, which is this, and the hash value of din? Can you find a relation between these two? Well, if you see, the relation is simple. You take the contribution of that substring in the original hash, which would be din, so it is din. This is the contribution of din in the hash of original string, right? You take that contribution and divide by p square. Why p square? See, I mean, can you find the relation why we are dividing by p square? Of course, because the index of d, which is the starting of the substring, is 2 in the original string, right? 0, 1 and 2. So we are dividing by p square to get the hash value of substring din, right? So this is the basis upon which we will be building our algorithm. You can take any substring and the hash value of that substring would be simply the contribution of that substring in the hash value of original string divided by p raised to the power index of first character in the first character of the substring. This is how we'll be calculating, but the problem is how to find the contribution, that is d times p square plus I times pq plus n times p raised to power 4. This would be an integer, right? Because d, I and n all will be converted to integer. This whole thing is actually an integer, right? I have already explained that in the previous lecture. So you can divide any integer by integer, right? And of course this is taken care, this is under modulo m, and you know there is the division operation is not allowed in modulo operation with modulo operation, so we'll be using inverse modulo. So this is the basic idea behind the algorithm. Now the implementation details. Now that we know how to calculate the uh, hash value of a substring, all you have to do, take the contribution of that substring in the original hash and divide it by p raised to power index of the first character of the substring, right? That is what we have to do, but how we are going to implement this, so let's see that. So we'll be using prefix array for saving the hash value of each prefix of a given string. This would help us finding the contribution of a substring in the original hash. How? Let me show you. So what I'm going to do, I'll be having a dp array. So dp of I would store the hash value of substring from 0 to index I. So if I have the string coding, then dp array would look something like this. Dp of 0 would store the value c times p raised to power 0. Dp of 1 would store hash value of substring from 0 to 1. You see, hash value of substring 0 to 1 is only co, and that is why in dp of 1 I am storing c hash value of co. Similarly for the rest of them. So using this you can calculate contribution of any substring in the original hash. How? For example, if I wanted din, right, din for the substring din, the L and R, the starting and the ending index of that substring are 0 1 2 3 0 1 2 3 4 2 to 4, right? So what you can do is the contribution of din in the original hash would be dp of 4 minus dp of 1, right? Starting index is 2, so we are not gonna subtract dp of 2 but dp of 2 minus 1, which is dp of 1. So dp of 4 minus dp of 1, if you would subtract from this whole thing, if you subtract this only, you will be left with din only. See, so for a substring L to R, the contribution of this would be the substring, how you'd be the hash value, how you'd be calculating. This is the contribution divided by p raised to power L, where L is the index of starting character, right, of the substring. So dp of R minus dp of L minus 1. This is how you'd be getting the contribution of the substring in the original hash. Now, if L is greater than 0, of course. If L is 0, you don't have to subtract anything, right? So this is how we'll be implementing the algorithm, and let me show you the implementation of this algorithm. You can go ahead and try yourself, and I'm going to you can pause the video if you want to implement yourself, otherwise I'm going to show you. So this is the input string for which we have to calculate or pre-process the dp array. And yeah, one more thing, you see here we have to divide by p raised to power L, but the problem is, since we are calculating modulo for hash, we are taking everything under modulo, right? This whole thing are under modulo m, but the problem is that with modulo there is no division operation. For that you have to calculate the inverse modulo. Whatever you want to divide with, calculate the inverse modulo of denominator, and instead of dividing, simply multiply that with modulo inverse of the denominator. So this expression would convert into dp of R minus dp of L minus 1 times inverse modulo of p raised to power L, right? So division is not allowed. Instead we have to find the modulo inverse, and after that multiply with the modulo inverse of the denominator. That is why we need to calculate modulo inverse as well. So here you see this is the input string. The tc is the number of test cases, L and R, of course, the left and the right indices of the substring for which we want to calculate the hash value. So I'm reading the input string and then calling the init function with the input string. So what I'm doing here is that I'm taking p, the prime, to be 31, and mode, that is my m, is 10 to the power 9 plus 7. So what I'm doing here is that p power this is almost the same as the code for string hashing that we have already seen in the previous lecture. So if you haven't seen the previous lecture, go ahead and watch that first. So This is inverse modulo. This I and V array stores the inverse modulo. So I and V of I would store the inverse modulo of p raised to the power I. So if I need to divide by p raised to power L, all I have to do is take, just a second, I and V of L that would store the inverse modulo of p raised to power L, right? So what I'm doing here is dp of 0 I'm already initializing. After that I'm running a loop from 1 to less than string size, each time finding the character and finding the next power of p and calculating inverse modulo. So this, at this point, it is p raised to power I. This thing basically store p raised to power I. I need to store inverse modulo of p raised to power I, right? And this is when I'm calculating inverse modulo of p raised to power I modulo mod. I have already explained modulo in how you would calculate modulo inverse in my number theory course series, so I'm not going to explain that here. Basically I'm storing the inverse modulo of p raised to power I, and after that since this is a prefix array, so I'm calculating the current contribution of the current character plus previous hash value of previous prefix plus contribution of current character. So basically dp of 5 would be dp of 4 plus contribution of current character, and that is exactly what I'm doing here. dp of I minus 1 plus contribution of current character. After the pre-processing, dp of I would store prefix of current hash value of substring 0 to I, right? After that there are tc number of test cases. Each time I'm reading L and R and printing the hash value of substring L to R. And how am I calculating? Simple. Simply, if result is equals to dp of R, if L is greater than 0, of course the result is equals to result minus dp of L minus 1, otherwise I don't have to subtract anything. After that, since I have to divide with p raised to power L, instead of that I'll be multiplying with inverse modulo of p raised to power L and taking modulo, finally returning the result. I'll be providing this code with the description in the description of the video, so you can go ahead and check out later for the reference. So if I show you, this is the code that we have written in the previous lecture. So let's see the result by these two. Just let me increase the font size, so it should be good. Okay, and this is this code we have written in lecture 3, and this is what we have written in this lecture. So I'm going to show you by comparing whether the results are same or not. See, lecture 4 substring hash, and this the other one that we have written in the third lecture. So for example, if I wanted to calculate the hash value of AB, it is going to be 63, right? So for this we have to pass a substring initially. So now suppose these many test cases are there. So first I want to calculate hash of AB, which is substring from 0 to 1, right? 0 to 1. See, okay, I'm also printing L and R, I guess. So let me just fix this. Just a second. I am printing L and R somewhere as well. Okay, I made the changes, but just a second, this is being compiled. Yep, so now here it is. Increase the font size. So let's see. So suppose the input string is this, and these many test cases I'm going to test on, and I want to find the hash value of substring 0 to 1, which would be basically AB. Substring hash value of AB is 63, right? Let's calculate for DEF. That would be 0 1 2 3 4 5. So 3 2 5 DEF. So DEF, see, the hash values are same. Let's calculate from 0 to this, the whole ABCD EF GH I. So 0 1 2 3 4 5 6 7 8. 0 to, sorry, let's calculate hash value of 0 to 8, which means hash value of ABCD EF GH I. So let's compare this with ABCD EF GH I. Hash value You see, these are matching. So I just want to show you that the algorithm that we have designed is working perfectly fine. And how much time is it taking to calculate hash value of substring? Is taking constant time, because the operation that you are performing are a constant time operation. They do not depend upon the size of the substring. They do not depend upon L or R or anything. That is why the algorithm the the way we are calculating hash of the substring of the initial string is only taking big of one time. While here, if you wanted to calculate uh, hash value of a string, you have it would take big of n time, where n is the substring size. So for each query it would require big of n time, while here for each query we are only taking big of one time. So this is the difference between these two algorithms. I'll be providing the code in the description, as I have already told. So yeah, this is all about this lecture. If you have any doubt or query, of course you can post it down in the comment section. So this was all for this lecture. Thank you guys for watching, and till the next video drops, keep coding. Thank you.